So we talked in class yesterday about what capacitors are. Now let's combine them as circuit elements within the same circuit. So again, in order to do this, what we're going to end up doing is basically we're going to recognize that Kirchhoff's rules are embedded in what we're going to come up with. So we're going to come up with a relationship for how you combine capacitors in parallel. We're going to come up with a relationship for how you combine capacitors in series. But all these are really sort of built on our two Kirchhoff's rules. So let's remember what those are first. So there's Kirchhoff's loop rule, which tells us that the sum of the potential changes across all the elements along any closed loop in your circuit must equal 0. We said really this is just a statement of conservation of energy. And then there's Kirchhoff's junction rule, which is that all the current that enters a junction must equal the current that leaves a junction. So basically just everything that comes in has to go out. And again, this is just a statement of conservation of charge. So we're going to use these two rules to build our rules for how you combine capacitors. So for starters, let's talk about capacitors that are connected in parallel. And again, we said in parallel, what that means is we've got a junction, and so whatever goes this way across element 1 can't go this way across element 2. The stuff is going to split. One will go across element 1, the other will go across element 2, and then it'll recombine back over here in terms of thinking about current. Well, so for capacitors in parallel, again, in order to set up our relationship for how we need to combine these mathematically, let's start by applying our loop rule. So the first loop I'm going to pick is I'll start here in this bottom corner and I'll go across the battery. And again, I'll notice that I'm going from the negative terminal to the positive terminal, so that means I'm increasing in potential. So this is going to be a potential increase. I'm coming across this capacitor, and notice that I'm going from the positive plate to the negative plate, which means that I'm going in the direction, so the electric field is going to point down within this capacitor. So I'm going in the direction of the electric field across the capacitor, which means that I have a potential decrease. And then that gets me back to where I started. So my loop rule, so this first loop I've got basically gives me that potential increase across the battery minus the potential decrease across the capacitor has got to be 0. All right, let's pick a second loop. So again, I'll start down here in this bottom corner, and this time I'm going to walk across the battery from negative terminal to positive terminal. That's going to be an increase. I'm going to walk across my capacitor from positive plate to negative plate, so that's going to be a decrease. And there's not anything else that I cross within that loop, so that gives me a second equation that tells me that the potential increase across the battery minus the potential decrease across my capacitor also has to equal 0. Well, I look at these two equations, and it's really easy to see that basically what this tells me is that the potential difference across capacitor 1 has got to be the same as the potential difference across capacitor 2, and both of them happen to be the potential difference across the battery in this case, because we have a very simple parallel circuit. But the important thing is that when I've connected my two capacitors in parallel, the potential difference across them is the same. So capacitors in parallel have the same potential difference. Okay? So let's use that piece of information and use our second rule. So again, here I have my circuit. Here's my junction. And so I notice that basically what am I going to do? Well, again, with steady state capacitor circuits, we're not going to talk about current, but we will talk about charges. And so what's going to happen when my two capacitors are fully charged is that I will have pulled some charge out of the battery. Some of that charge will have gone down this branch to now charge capacitor 1. The rest of that charge will have gone down this branch to charge capacitor 2. When I think about sort of redrawing this as my equivalent capacitance, well, I know that here's my equivalent capacitor. And so basically, again, what I recognize is that all the charge that gets pulled out of the battery, all of that's being stored on my equivalent capacitor. And then again, if I think about my loop rule with respect to this simple circuit, again, it tells me that the potential across my simple circuit, the potential across my battery has got to be the same as the potential across my equivalent capacitor. So I can use this information and sort of applying what we'll call the junction rule here, that even though this isn't current, we're still keeping track of charges. And so what this tells me is that the total charge that I'm putting on my equivalent capacitor has got to be equal to the charge that gets stored on capacitor 1 plus the charge that gets stored on capacitor 2. When I use my fundamental rule for capacitors, so I can simply write this as CEQ times the voltage of the battery, right? My equivalent capacitance times the voltage of the battery, that's got to be the charge on my equivalent capacitor. Well, the charge on capacitor 1 is just C1 times V, plus the charge on capacitor 2 is just C2 times V. And again, this is really C1 V1, this is really C2 V2, but we've already seen that V1 is equal to the potential across the battery, and V2 is equal to the potential of the battery. And you look at this equation, and it's easy to see that, oh, voltage just cancels out. And so I'm left with a rule for how to combine capacitors in parallel. So the equivalent capacitance of two capacitors in parallel, combining two capacitors in parallel, is simply adding their capacitance. Now, one nice thing that I can use to check about this is that, well, if the equivalent capacitance has got to be equal to C1 plus C2, then that tells me that the equivalent capacitance in this case has got to be greater than either of those individual capacitor values. So if this is a 1 nanofarad capacitor and this is a 2 nanofarad capacitor, I know that when I combine them, I've got to get something that's larger than either of those two values. And sure enough, 3 nanofarads happens to be larger than either 1 or 2. Alright, so this is connecting capacitors in parallel. Now let's come back and connect them in series. And so again, when we talk about current, right, we say current traveling through element 1 must travel through element 2. And so sure enough, when I take my two capacitors as they're charging, right, we would think about the current coming through one as coming through the other. But mostly, again, this is just a situation of where I've combined two capacitors in series, which means there's just nowhere else for the current to go, for the charges to go. And in fact, from the perspective of the battery, what's very interesting when I combine two capacitors in series is that the battery basically sees a positive plate here and a negative plate here. It doesn't see any of the rest of this. So from the battery's perspective, it's saying there's only a single capacitor here, and I'm putting plus Q up on this one and minus Q down on this one. And then what's happening is that, or from the battery's perspective, what's happening is that we are then taking a neutral conductor that happens to be this other plate and a wire and this other plate, and now that neutral conductor is responding to the charge that the battery is putting on the two outside plates. So what this means is the battery is going to put plus Q up here, minus Q down here, and then when we put in our neutral conductor, basically meaning the rest of our capacitors, well, this plate will charge with minus Q in response to this plate's positive Q, and this plate will charge with plus Q in response to this plate's minus Q. And so the important thing you see is that the charge on capacitors that are put in series is the same. So there's a very, so when we take two capacitors and combine them in series, what's the same on those capacitors is the charge. Alright, so let's use this information in our loop rule. So now I know that my capacitors in series carry the same charge. So when I apply my loop rule, well, again, I can think of applying the loop rule here, or I can think of applying the loop rule over my combined circuit. When I apply it for my circuit on the left, basically what I get is, well, I start down here in the bottom corner. I'm going to walk across the battery from negative to positive, so that's going to be an increase. I'm going to go from positive plate to negative plate across capacitor 1, so that's going to be a drop. I'm going to go from positive plate to negative plate across capacitor 2, so that's going to be a drop. So I end up with this equation for my loop rule. I just take the V1 and V2 over the other side, so here's what I've got. And now when I look at this the voltage of the battery, well, I'll notice that that happens to be the same, thinking about my loop rule over here, that the voltage of the battery happens to be the same as the voltage across my equivalent capacitor. Notice it's not the same as the voltage across my two capacitors over here, right? Because if I lost all of the voltage of the battery across capacitor 1, that would mean there'd be nothing left to lose over C2, and that doesn't work in terms of this equation. So my voltages here are not equal to the voltage of my battery. But the equivalent capacitor, again, my loop rule here tells me that the equivalent capacitor, combining these two, that has to be equal to the voltage of my battery. So I can write the voltage of my battery as the charge on my equivalent capacitor divided by the equivalent capacitance. So this is just using our fundamental rule, Q equals CV, where now I'm just solving for V. And again, for V1, well, I know that's going to be Q1 over C1, and here Q1 also happens to be equal to Q. V2 is just going to be Q2 over C2, but again, I know that I've put that same charge Q on capacitor 2, and so again, you notice that because all these capacitors share the same charge, I've got the same Q on top here, that just cancels out, and I'm left with my rule for combining capacitors in series. So this is 1 over the equivalent capacitance is equal to 1 over capacitor 1 plus 1 over capacitor 2. Now, a couple of things to sort of keep in mind here. One is we have a very simple check, and that's that the equivalent capacitance when I combine capacitors in series now has to be less than either C1 or C2. The most common mistake students will make is that they will solve this equation and forget to invert to get the equivalent capacitance. So one of the things that we'll try to very strongly emphasize in class is that you've got to remember, if you're going to use this equation to combine capacitors in series, that the equivalent capacitance requires one more step of inverting your answer when you combine 1 over C1 plus 1 over C2.